Okay, so let's get started. Good afternoon, everybody. Thank you for coming. Well, I have a pretty long title right here with a lot of jargons to process, but at this point, you only need to grasp the first word and the last word. So today I'm going to talk about seismic inversion. But first, let's get started from this cover picture. These soldiers in this picture are called the Hessians. They were German mercenaries, or the so-called auxiliaries, fighting alongside the British Redcoats during the American Revolutionary War. They have something around 30,000 troops, comprising a quarter of the British land forces. Actually, George Washington's famous crossing of the Delaware River was to fight against the Hessians in the very next day. They are called the Hessians because 65% of them come from the German principalities Hesse-Kassel and Hesse-Hanau. And these Hessians are actually very powerful troops. In their first engagement of the war, they played a decisive role in the victory of the Battle of Long Island. But for the British, this power comes with a price. To run the troop from Hesse-Kassel, the British Crown was charged roughly equal to 13 years worth of taxes of that state. So this is the Hessian in the military, a powerful and expensive army. Now let's switch gear to talk about the Hessian in mathematics, where the Hessian is defined as the second order derivative of objective function. It is named after the German mathematician Ludwig Otto Hesse. And this mathematical Hessian surprisingly inherits the properties from its military counterparts. It is powerful and it is expensive. Please keep that in mind. Let's first see the power of Hessian using a very simple math example. And here's an objective function, phi of x, which means we want to minimize this function phi by finding the optimal x. And clearly, this function can only reach its minimum when both terms equals to 0. So x1 equals to 1 and x2 equals to minus 1. Then the target optimal point, x star, will be 1 minus 1 right here. And we start from the initial location, the origin, 0, 0. And we try to navigate to this target right here. And then there are different, hold on, did I turn on my video? Oh, okay. Okay, now we're good. Okay, so there's different delta x would be 1 minus 1 as well. Now think about it. You're standing high on the Mount Nittany. So what is the best direction to go downhill to the Happy Valley? Well, one good option would be to go along the steepest direction downwards. Mathematically, this means this direction, we call it P1, is the negative gradient minus g. And in this case, it turns out to be 2, 0. So the steepest direction, P1, tells us to go along the horizontal axis. But the target is right here. So this direction is fair, but it is not good enough. So again, high on the Mount Nittany, it seems a little bit of short-sighted to only consider the steepness, namely the gradient right here. You might also want to incorporate the curvature of this mountain, indicated by the second derivative, namely the Hessian. In this case, the Hessian is a 2x2 matrix, 4, 2, 2, 2. Note that for a quadratic problem, we have this relation, h delta x equals to P1. And of course, we would love to go along this delta x direction. We call this direction P2, which is h inverse P1. And if we plug in everything, we got 1 minus 1 right here. So the gradient-based direction P1 is kind of close, but this Hessian-based direction P2 takes us directly to the Happy Valley, the optimal point. And this is the power of Hessian. Let's get back to seismic. Generally, when we analyze seismic waves penetrating the Earth's interior, we usually end up with the seismic velocity model because the velocity can indicate different physical properties, including like composition, temperature, water saturation, etc., etc. In the meantime, the seismic attenuation, which measures how fast the seismic wave decays, it is another good indicator of physical properties. Here, I show a global lower mantle model. The first row is attenuation, and the second row is velocity. The two columns are different cross-sections. As we can see, the velocity and the attenuation do not necessarily correlate with each other. So if we have independent estimation of both attributes, we can have a better constraints of the Earth's interior. And this is the ultimate goal of our work, which is to produce reliable and independent velocity and attenuation models simultaneously. And we do that with a method called full waveform inversion, the FWI. For example, say this is the ground truth of the Earth. When an earthquake happens, we can observe a seismogram like this, the data. And starting from some initial model, and using which we generate some synthetic seismogram shown by this blue trace right here. Apparently, the data and the synthetic are not the same because our initial model is different from the ground truth. Then we map this data residual back to the model and iteratively refine the initial model, trying to minimize this waveform residual and approach the ground truth. This process is the so-called full waveform inversion, the FWI. Well, so far everything looks good, but we will have some common problem in this process when we are after multiple parameters. Check out this example. So these are our target models, the ground truth. The left is velocity denoted by c, and the right is attenuation denoted by gamma. So both of them have homogeneous background and a circular anomaly at different locations, right here and right here. And we start from homogeneous initial models without these anomalies, and we can compute the steepest direction, P1, namely the negative gradient, as in the mass example. And this is what we got. The left-hand side is velocity direction, and the right is attenuation. Let's compare to the target model. So this is the target model, this is the P1 direction. We can see that the velocity anomaly can be captured by this velocity direction P1. And actually, this attenuation direction anomaly can also be captured by this attenuation direction. But the problem is that this velocity anomaly is mistakenly mapped to this attenuation P1. And this is the so-called crosstalk artifact. And the goal, or the motivation of this specific study is to mitigate this kind of crosstalk artifact. So far, we only use the first derivative, the gradient. In fact, the second derivative, the Hessian, is expected to give us a hand on that. Let's see what the FWI Hessian looks like. Remember in the mass example, we have like two parameters, x1 and x2, and the Hessian is a 2x2 matrix. Now our model has n grid points, and each grid point has two parameters, velocity and attenuation. So we will have like altogether two n parameters. The first n are velocity c, and the rest are attenuation gamma. So this Hessian will be 2n by 2n matrix. And it has a block structure. The four subblocks are HCC, HC gamma, H gamma C, and H gamma gamma respectively. So this is what Hessian looks like. Now let's see why we care about Hessian, or how the Hessian matrix is related to the crosstalk artifacts. As I have mentioned that for a quadratic problem, we have this relation, H delta X equals to P1. In this example, H is the Hessian matrix with this block structure, and delta X is the difference between the target and the initial models, namely the anomalies, and P1 is a negative gradient, which has crosstalk artifacts right here. And we are wondering where these crosstalk artifacts come from. We can expand this expression into two separate equations, like this. So intuitively, this velocity P1 and this attenuation P1, both of them are weighted summation of both velocity anomaly and attenuation anomalies. And the weights are determined by the subblocks of this Hessian. In particular, the reason why we have a crosstalk right here is because this cross term is large enough that it is comparable to this attenuation term. So the velocity anomaly will be reflected on the attenuation direction right here. And this crosstalk information is embedded in this Hessian subblock, H gamma C. And this is how the Hessian matrix is related to the crosstalk. So the next question would be how to get rid of it. Let's transform it back to this compact form and see how to incorporate the Hessian. Well, it is pretty straightforward to put this Hessian on the right-hand side. And ideally, we can directly jump to this target model as the mass example I showed at the beginning. But note that this relation only holds for quadratic problem. And in general, this FWI is much more nonlinear than quadratic. So we won't be able to recover this delta x in this way. Instead, what we got is a search direction P2, which is still much better than P1, as in the math example. So far, I have only talked about the powerful side of Hessian, and here comes the expensive side, just as the Hessian soldiers. Think about the dimension of this matrix. It is 2n by 2n, where n is the number of grid points, which would be hundreds of thousands in practice. The additional cost to compute each single column of this Hessian would be 2 simulations per source. So it has 2n columns, and altogether we will have a cost something around 4n. In addition, we need to store this huge matrix, and we even need to invert it. The cost of them would be astronomical and prevent it from practical applications. But we have a good news, is we actually have a workaround. We can put the Hessian on the left-hand side and solve this linear system approximately. Intuitively, it's like we try different P2 until the left-hand side approximately equals to the right. And actually, we can do a little bit more complicated or more sophisticated than that. Instead of like random trying, we adopt this so-called Newton CG method, which uses an inner CG loop to solve this linear system approximately. At each CG iteration, or say each time we try a different P2, the cost is something around 2 simulations per source. And we only need around a handful of iterations thanks to the CG, which leads to the cost something around 10. Compared to the 4n, this is surely acceptable. And this Newton CG method is what we use in this study. Okay, now let's get back to our example. This is the target model, and this is the P1 direction, the gradient-based direction. We have the crosstalk right here. And by incorporating the Hessian, we have the P2 direction. Let me flip back and forth. So this P1, P2. We can see that by incorporating the Hessian, the crosstalk has been significantly mitigated. And this is one single iterations. After 20 iterations, these are the final models we got. Let's compare to the target model. So these are the target models, final models. We can see that by incorporating the Hessian in this way, we have a very nice delineation of both anomalies with hardly any crosstalk at all. Some take-home messages. We have shown that just like the military Hessian, the mathematical Hessian is powerful, but it is expensive. Unfortunately, we can incorporate this Hessian via this Newton CG framework, which is pretty much affordable. In this way, we developed this Hessian-based FWI algorithm to invert for both velocity and attenuation models simultaneously. And by incorporating the Hessian, the crosstalk can be significantly mitigated. Well, the velocity and attenuation are like intertwining with each other, just like the yarn ball shown right here. And with the help of Hessian and the financial support from the DOE and the NSF, who I would like to acknowledge here, we hope to untangle this mess of yarn into a clean velocity model and a clean attenuation model. And that'll be all for my presentation. I will be happy to take some questions.